Coulomb's law of electrical force, scalar and vector form. This is what we are going to learn in our today's video. As we know, if 2 point charges are kept in some medium, the medium, it could be anything, keeping at some distance r. Keeping at some distance r means these two charges are kept at some distance. Okay, now there will exist a force between these 2 point charges. That force is called electrical force. Now, what will be the magnitude of that electrical force that will existing between these 2 point charges, and what will be the direction of the force that will existing between these 2 point charges? It's given by a law which is called Coulomb's law. So usually Coulomb's law of electrical force, we have two form. One is scalar form of Coulomb's law, another one is vector form of Coulomb's law. Scalar form of Coulomb's law, it gives the magnitude of the force that will exist between these 2 point charges. That means this scalar form gives us the magnitude, and what will be the direction of these forces that will exist between these 2 point charges. So that is obtained by a Coulomb's law of vector form. So usually vector form, it not only gives the magnitude of the force between these 2 point charges, but it also gives the direction of the force that exists between these 2 point charges. So let's start with the Coulomb's law of electrical force with the scalar form at first. So in order to understand Coulomb's law, so let us take 2 point charges Q1 and Q2 kept at some distance r in any medium. So medium, it could be anything. Now obviously the force will exist between these 2 point charges. Okay, and the force, it may be anything. It may be attractive or it may be repulsive. It depends on the type of the charges we are taking it. Okay, it means like if these two charges are like charges, that means the force that will be existing between these two charges, it will be repulsive. And if the two charges we are taking it as a negative charge, then the force that will exist between these two charges, it will be attractive. Okay, so now let us, by considering this, now let us start the statement in the Coulomb's law. So what the Coulomb's law says, it says electrostatic force. So let us take electrostatic force it as F. So according to this law, between 2 point charges, now point charges mean what? Point charges means the magnitude of these two charges, it's quite less comparable compared to the distance between these two charges. Okay, so in that case, these two charges are termed as point charges. Okay, so electrostatic force, means electrostatic force between 2 point charges is directly proportional to the, so I'm writing directly proportional to the product of their magnitude. That means I'll write product means multiplication, so I'm writing product of these 2 point charges. And the second one, it says it and inversely, so that electrostatic force, again, it is inversely proportional to the square of distance between their centers. So this is the distance between their centers, which is r. So obviously it should be 1 by r square, because it is inversely proportional to the square of the distance between their centers. Okay, so between their centers means here the distance, actually this line, actually it is a line joining the center of these two charges. This is what it does mean. It actually means which means like distance between their centers. Okay, now if I combine this 1 and 2, so if I combine this 1 and 2, combining 1 and 2, what I get, I'll get f proportional to the q1 q2 by r square. Okay, now in order to take out, what I have to do, I have to take out this proportional sign. So I should give one equal. In order to give this equal, I need to write one constant. Okay, so proportional constant I have to write here. That constant is k. Here that constant is k. Now what is k in this case? K is called the electrostatic force constant. Here, what I can say here, k is called electrostatic force constant. Okay, so I'm writing k is electrostatic force constant. All right, so k is electrostatic force constant. Now the value of this k, the important thing, okay, the value of k, it depends on the medium in which the charges are kept. Okay, remember this value of k, it may be different for different mediums. Say suppose if you keep these charges in water, if you keep these charges in water, the value of K, it would be different, okay? And if you keep these charges in, say, suppose in air, it will be again different. The value of K, it will be different, okay? So usually the value of K actually depends on the nature of medium in which the charges are kept and the system of unit use. And the system of unit use, that means whether you are using SI units or whether you're using some other system of units, okay? So usually the value of K, it will be different for different medium in which the charges are kept and the different system of units which you are using, okay? For standard, and what we do, we'll take these two charges are kept in air, and we'll take the SI unit, okay? We'll take the SI unit. So let me write that thing here. Well, let me take that thing here for air, okay? For air or vacuum, or I could say free space, okay? Or I could write free space, okay? So for air oblique vacuum or for space, um, and for SI unit, okay? So what I'm doing, so we have taken what? We have taken air and vacuum as the free space. That means in these charges, there is a medium called air or vacuum or free space, and for SI unit. So we are using the unit as SI unit. In that case, what would the value of K? That is important. What would be the value of day? Okay, so let me write that thing here, okay? So in that case, what will be the value of K? The value of K in that case, it would be 1 by 4 pi epsilon naught. Okay, let me write this as equation number 3. Okay, equation 3. So this K value, it would be 1 by 4 pi epsilon naught. Okay, so under which case? Under the case in which the charges are kept in air or vacuum and the system unit is SI unit. Okay, so in this case, now what will be the value of K? Now let me try to find out the value of K. So let me take the pi value as 22 by, okay, let me write it over here. Okay, so I'll get more space. So let me write it over here, 1 by 4. I'm writing pi value as 22 by 7. Okay, now what is epsilon naught here? This is also important. Okay, what is epsilon naught? Epsilon naught in this case is called the absolute permittivity of free space. Okay, where you remember, I'm writing this one over here. Okay, where epsilon naught is, okay, absolute, you remember, it's absolute permittivity, okay? Absolute permittivity of free space, remember, okay? Now, what is permittivity? Permittivity actually is nothing but the property of a medium. Any medium. Remember this permittivity, absolute permittivity, it will not only for air or vacuum or free space, okay? This absolute permittivity, it will be for other medium as well, like water also, it have some absolute permittivity value. For mic also it will have some absolute permittivity value, okay? But since here we are using free space, so I'm writing epsilon naught, which is actually absolute permittivity of free space. And permittivity actually, it is the property of a medium, okay? Remember, I'm writing it over here, okay? So permittivity actually, it is a property of a medium. Remember, it's a property of a medium, okay? It's a property of a medium which affects the magnitude, which affects the magnitude of force between 2 point charges. Magnitude of force, okay, between 2 point charges. Remember, between 2 point charges, this you keep it in your mind. That means this permittivity will have that property. It has an impact on the magnitude of the force that will exist between these 2 point charges, okay? So this is what actually the permittivity, okay? Now, so epsilon naught is actually absolute permittivity of free space, and the value of that epsilon naught, actually it is 8.854 into 10 to the power minus 12, okay? Coulomb square per Newton, okay, per meter square. All right, so if I take these values and if I put it over here in place of epsilon naught, so let me put this value 8.854 into 10 to the power, okay, minus 12. All right, so now I'll put Coulomb square, okay, per Newton, okay, per meter square. So what I'll get, so if you calculate this value, you can calculate, okay, you can calculate separately, okay. You will get exactly 9 into 10 to the power 9, okay. You'll get exactly 9 into 10 to the power 9. And if it goes on the numerator, per Newton will become Newton, per meter square it will become meter square, and Coulomb square it will become per coulomb square. Okay, so this is what we get the value of K. If I put all those values, 4, 22 by 7, and absolute value, will get this value. Okay, and this is the unit of K. Okay, this is a unit of K. So don't get confused how we are getting this unit of K. Actually, let me write, let me tell you how we get this unit actually. Okay, so let me do it here in the rough. Let me do it here in the rough. Okay, so actually what we know from this, you can check it here. F equals to K Q1 Q1 Q2 by R square. Okay, F equals to K Q1 Q2 by R square. Okay, so what I can write, K I can write, okay, F into R square is F into R square. All right, Q1 Q2 comes in the denominator. Okay, now what is the value, what is the SI unit of force? It's Newton. What is the SI unit of distance? It's meter, so it will become meter square. Now the SI unit of charge is coulomb, so coulomb into coulomb square. So how much we are getting, my dear friend? We are getting Newton meter square per coulomb square. This is what I'm writing it over here. Okay, Newton meter square per coulomb square. I hope you got my point. Now now let me make you understand now how we can put these values over here. Now from equations 3, if I put this value, how much I'll get? Okay, I'm doing in the next paper. You can pause the video and you can jot down. So okay, so what we got now? So equations 3. Now from equations 3, I'm writing from equations 3. What we got in equation 3? Equation 3 is F equals to K Q1 Q2 by R square. And since we have taken the medium as free space, air, or vacuum, for that we get the value of K is 1 by 4 pi epsilon naught, because we have a unit, use the unit as SI units. In that case, we are getting the value of K as 1 by 4 pi epsilon naught. So if I put that value, I'll get 1 by 4 pi epsilon naught Q by Q2 by R square. Okay, so the value of F we are getting it as, now this value I'm getting how much? I got how much? We got this value as 9 into 10 to the power 9. So I'll write here 9 into 10 to the power 9. So Q1 Q2 by R square we are getting. Okay, so actually what it gives us, it gives us now this F, it will gives us the magnitude of the force that will exist between these 2 point charges. Okay, magnitude of the force. But remember one thing, this is a case where I have taken medium as what? Free space. Okay, and the system of unit use, we have used SI unit. You keep this thing in your mind. Okay, this value, it will be different. Remember, if I take this medium as water, and if I take system of units different, or you can or it may be different for any other medium like mica, glass, whatever. Okay, so in this case it is 9 into 10 to the power 9. Why? Because we have taken the medium as free space, and for SI unit we have used. So in this case we are getting this value is this. So it means that this equation actually it gives the magnitude of this force between these 2 point charges. Okay, so this is called the scalar form of Coulomb's law. So this equation actually generally it is the scalar form. It is the what? Equation. It is the what? It is the scalar form of Coulomb's law. Why this is a scalar form of Coulomb's law? Because this equation only gives the what? Only gives the magnitude of the force between these 2 point charges. I hope you got my point. Okay, and remember this k it will be different for different system of units and different nature of the medium. Okay, so remember, don't think that this k will be same for every kind of medium. Okay, here the value came 9 into 10 to the power 9 because we have taken the medium as free space and the system unit is SI units. Okay, so don't forget this. So this is called Coulomb's law in scalar form. Now let us know Coulomb's law in vector form. Let us move to another topic. It's called Coulomb's law in vector form. So Coulomb's law in vector form. So let me write this as Coulomb's law in vector form. Okay, this one is also a very interesting topic. Okay, Coulomb's law in vector form. Why this Coulomb's law in vector form? Because the first law only gives the magnitude of the force between these 2 point charges. It doesn't give the direction of the force, but since force is a vector quantity, it will have a direction as well. So how to get the direction of that force? That is given by this Coulomb's law in vector form. Okay, so to understand the vector form of Coulomb's law, let us take 2 point charges, like charges. Let us take two like charges. Okay, again I've taken two like charges. This is q1, this is q2. We have taken two like charges, and let us keep these two like charges in free space or air. air or vacuum. Okay, so we have taken the standard medium. All right, we have taken the standard medium. So let us think q1 and q2 are the two like charges. So one thing you have to keep it in your mind here. Here q1 and q2 are what? We have taken like charges. We have taken like charges. All right, we have taken like charges. Okay, another point, we have taken what? This medium, we have taken what? Medium is what? Medium is what? Medium is free space. We have taken free space or air or vacuum we have taken. All right, don't forget this. So since q1 and q2 are like charges, it means there will be an repulsive force between these 2 point charges, because the q1 and q2 we have taken the like charges. All right, now in this case, you remember, in this case what happens actually is that this charge, okay, q1, it will exert a force on charge q2. Remember, okay, this q1 will exert a force on charge q2, and since these two charges are like charges, so the forces, it will be repulsive. So let me denote this direction of force like this, because it is repulsive. All right, now since it is a force on charge q2 due to charge q1, so I'm writing it as f21. It means force on charge q2 due to charge q1. Remember this, okay, don't forget this. All right, in the same way, what happens, this charge q2 will also exert a force on charge q1. Okay, and the force, it will be repulsive again. So this will, I'll denote it as f12, which means force on charge q1 due to charge q2. Remember, don't forget this. All right, so let me write this whatever I've explained over here in language here, so that you can jot down in your notes. All right, so let f21, all right, let f21 equals to force on charge, force on charge q2, all right, due to charge q1, due to charge q1. Okay, and this f12, what I'll write, f12, force on charge q1. Okay, force on charge q1 due to charge q2, due to charge q2. All right, now one more thing is there. Again, one more thing is a very, very important. Okay, what happens actually, there is a, this force is in this direction and this force is in this direction. All right, to denote this direction, we should have one unit vector also. Let me make you understand this with another thing. Okay, rough, I'm doing in the rough. Okay, usually it's also in mathematics, and also in class 11 you learn in physics. Okay, we know that if a unit vector, actually a unit vector, okay, a unit vector, we know that in the direction of any vector, in the direction of any vector, in the direction of any vector, what you have learned a cap means unit vector. It is given by like this, right? We have learned this one, right? It's a vector a, and this is a mod a, which means the magnitude of vector. It simply means vector a is nothing but magnitude of the vector together with the unit vector. Okay, what actually it means, it means that any vector, for any vector, this will gives the magnitude and this will gives the direction. This unit vector, actually it is attached with this magnitude in order to indicate the direction of this vector. Okay, so in language, what I can write this one as wait, this is not magnitude. Okay, let me write with another color. Okay, another color. All right, so okay, so this is vector. All right, so vector, it will be magnitude. Okay, it will be magnitude. As you can see, this is your magnitude. All right, magnitude. All right, and this is a unit vector. This is a unit vector. So generally, as you can see here, a vector, it's attached the magnitude together with the unit vector. Why this unit vector is attached with the magnitude? Because in order to show the direction of this vector, this unit vector we use, actually unit vector we use in order to show the direction of a given vector, because it has a magnitude 1, because we know that any unit vector, it has a magnitude always 1. It has always a magnitude 1. Okay, so simply with the magnitude 1, it will not affect the magnitude of this vector. Understood? Only it will affect in the case of direction. So that is what we want. We want the direction of the vector. So that's the reason we attach this unit vector with the magnitude of the given vector. Okay, this is what actually I wanted to tell you. In the same way, what happens here, this force F21, it's a force on the charge Q2 due to charge Q1, and it will have some direction. So as you can see clearly in this case, the direction is from charge Q1 to Q2, and in order to indicate that direction, now I will take one I'll take one unit vector, that is r cap 1 2, which means direction. Okay, you can see direction pointing from q1 to q2. Okay, or you can say unit vector pointing from, it would be better, it would be better, I'll write here unit vector. Okay, all right, unit vector. Okay, unit vector pointing, all right, pointing from charge, okay, q1 to q2. Okay, in the same way, so remember this r12 is pointing from charge q1 to q2. All right, r12 is pointing from q1 to q2. All right, in the same way, this force f12 will have also some direction, and it is pointing you, as you can see, from q2 to q1. Okay, so q2 to q1, this is pointing in this case. Okay, so all right, this r21 is also a unit vector pointing from charge. Okay, pointing from charge q2 to charge q1. All right, now if I need to get what is the magnitude and as well as the direction of this force between these 2 point charges, now let me know what is the direction, what is the magnitude and direction of this force, what is the magnitude and direction of this force. If I use the Coulomb's law, what I'll get F21, it is equals to 1 by 4 pi epsilon naught. Why 1 by 4 pi epsilon naught? Because we have taken air, no, medium as free space, air, or vacuum, and we have used SI unit of system. Okay, so it's 1 by 4 pi epsilon naught. Okay, so q1 q2 r square. Now force is a vector, now this gives the magnitude, this is the what magnitude. So for this particular vector, okay, this will gives the magnitude, but what is the direction of this vector? For that I need to attach one unit vector with it. So what is the direction of this f21? You can see it's from q1 to q2, and that is denoted by a unit vector r12. So I'll attach here r12. So now this is my complete expression, which shows magnitude with the unit vector. You can see magnitude with the unit vector. Okay, so vector, so f21 is a vector, magnitude with the unit vector. Now this will gives the magnitude together with the direction. In the same way, I'll also get f12, same value, 1 by 4 pi epsilon naught q1 q2 by r square. All right, now what is the direction will be from this charge q2 to q1, and it is denoted by a unit vector r21. So I'll write it as r21. Okay, so this gives me the Coulomb's law in vector form. Now as you can see, these two expression easily gives us not only the magnitude of these two forces but also the direction of these two forces. Now, and this is called the Coulomb's law in vector form. Okay, so so this is our Coulomb's law in vector form, and this is our Coulomb's law in scalar form. But one more thing I want to tell you, please be in the video. It's a very important thing, and now I'm going to tell you. Important thing is like importance of vector form. Okay, there's an some importance of vector form. All right, importance of vector form. Vector form has some importance, okay, as compared to the scalar form. Now, so what is the importance of that vector form? So let me tell you. Okay, number one, the vector form actually it not only gives magnitude together with the direction, but uh, uh, it says some informations as well. So let us know what are those information. Number one is that the vector form shows, the vector form shows okay, the forces, all right, the forces f21 and f12. Okay, forces f21 and f21 are, okay, um equal and opposite, which means equal and opposite means, it means like this forces also obeys Newton's third law. It also says that. Okay, let me make these things clear. Okay, as we know what we got in our f21, we got this one value. Okay, so I'm writing these two values here. What we know, f21, it is equals to 1 by 4 pi epsilon naught q1 q2 r square, and direction is r12 with the unit vector. Okay, now if I make the simplification of this, r12, if I keep on the left hand side, what I'll get, I'll write this F21 on the numerator, this whole thing's in the denominator. Okay, I'm just doing the simplification over here, so don't get confused. Let me make this as equation 1. And similarly, what we know F12, just now only we got F12 is 1 by 4 pi epsilon naught Q1 Q2 by R square R21. This from where we got, you see F12 is this much, right? This is what I've written over here. Okay, so don't get confused with this. Okay, so again, if I keep this R21 on the left hand side, I'll get F12 divided by 1 by 4 pi epsilon naught Q1 Q2 by R square. Okay, this is equation number 2. Now you can see here in this case, this R12 and R2 are an equal and opposite. These unit vectors are equal and opposite, and they are having same magnitude, right? Because unit vector usually they have a magnitude of 1, so in that case, what I can write, since I can write, since let me write with another color, since I can write R12 unit vector is equal and opposite to this R21 unit vector. Okay, so now if I put this values R1 to these values here from 1, equation 1, what I'll write, F21 as 1 by 4 pi epsilon naught Q1 Q2 by R square. Okay, and this R21 I can write it as F12, okay, divided by 1 by 4 pi epsilon naught Q1 Q2 by R square. Okay, now if I just cancel out these things, how much I'll get? I'll get F21 equals to minus F12. Okay, so this is what does it mean? It means that two forces are equal and opposite, which means that these forces obeys Newton's third law, because from Newton's third law we know that to every action there's an equal and opposite reaction, right? So this is what we got, an important information from this vector form. This is number one information. There's one more information. This actually the vector form says. Okay, let me tell you that one also. Okay, as you can see, since F1 to F21, all right, this is not F21, it's wait, this one F21. All right, as you can see, F21 is minus F12. What does it mean? Actually, it means actually the two forces are acting along the same line. It means that two forces are acting along the same line. All right, because we know that now, if this, let me tell you, if these two forces are somewhere like this, okay, can you say these two forces are acting along the same line? No, in that case you cannot write F1 it is equals to F2. It will be wrong. You getting my point? It is wrong. You cannot write like this. But if they are acting along the same line, that means you can see in this case two forces are acting along the same line. You're getting my point? You're getting my point? So this is the meaning. Actually, this particular thing, it says two forces are acting along the same line, which means what? Which means forces are acting, which means that forces are acting along the same line. Forces are acting, okay, along the same line, along the same line. And if they are acting along the same line, what does it mean? It means the two forces are central forces. Why? Because the forces are acting along the line joining the center of two charges. This is what I wanted to tell you. That is acting, acting along the line joining, acting along the line joining center of two charges, line joining center of two charges. All right, line joining the center of two charges. Okay, this shows that electrostatic force between 2 point charges is a central force. This shows that electrostatic force, okay, between 2 point charges, 2 point charges is a central force. All right, intercharges is a central force. So as you can see, so this vector form not only gives the magnitude and direction, but also it so gives this information, important information. This is number one, the forces are equal and opposite, which means they also follows the Newton's third law of motion. And the second one is according to this, we can say this electrostatic force that exists between 2 point charges is a central force, because central force is a force which acts along the line joining the center of two bodies. So this is what we call the importance of vector forms. So I hope you like the video. Okay, and if you like my video, and if you want to get this kind of same videos in the coming future as well, please like, subscribe, and give a good comment in my channel. Thank you.